Okay, this time let's work on obtaining equations of motion using Lagrange's equation. So previously we worked on drawing free body diagram and obtain the equations of motion using Newton's law, right? But for the Lagrange's equation, you don't have to consider the force, the free body diagram because you're going to basically working on the energy, which is a scalar parameters. So there are three basic steps for the Lagrange's equations. Like first, you should figure that out what's going to be the what is the generalized coordinate, and second you have to define the kinetic and potential energy, and you can just put it into those values for the Lagrange's equation. Generalized coordinate itself is the coordinate that uniquely describe the rigid body motion with the minimal number. So for example, if I want to describe the center of mass, usually x and y components will be a good candidate for that. However, is your x is independent for the y? Well, actually no. If you are moving forward, your x is going to the left, but setting the minus value, then your y value will decrease, right? Because the length, your body length doesn't change. So in this case, even though you have a x and y two components, it's only dependent on by the theta, right? So if the x is fixed, then x is determined, the y has been determined as well. So for example, if I define the tilt angle theta here, your x and y components will be expressed by a sine theta and cosine theta. So you have only one parameter that can uniquely describe the center of mass position, which is theta. Here, the theta is what we call the generalized coordinate. Okay, once we set the generalized coordinate, we have to formulate the kinetic and potential energy. So kinetic energy for the rigid body is what? Described by the linear speed, the linear velocity square, the mv square, and the rotational velocity square, I omega square, right? And your, oops, it's a typo. Your potential energy due to the gravity with respect to this flat surface will be mgl cosine theta. Is that correct? Well, if you're on the stationary ground, yes. However, here the people is on the moving cart with the velocity v naught. So your linear velocity, the kinetic energy is not this theta dot L theta dot term only, but you have to also consider the kinetic energy contributed by the cart velocity movement, right? So your total kinetic energy will be m total v linear square, which is L theta dot plus VO. Okay? Now, then you can plug in those to the Lagrange's equation, what the Lagrangian defined by T minus V, and you have a derivative for the Q dot. Here's a theta dot, and around L, round Q. And also, if there's external force, you should also consider for that. Okay, so let's drive the Lagrange's equation further to end up getting the equations of motion. So you have, again, the generalized coordinate to describe the center of mass in terms of theta. And you have a kinetic energy, which has a term for L theta dot term, the linear velocity components for the bar with respect to the ankle joint. However, since you're on the moving platform with the velocity VO, you should also consider for that and angular velocity components here, and you have a gravitational potential energy. And for the Lagrangian, you can do the round L round Q dot. Here is a theta dot, round L round Q, which is a theta. And note that your L, which is T minus V, has only velocity component for the kinetic energy term, right? So this can be rewritten as round T round Q theta dot, and both kinetic energy and the potential energy has a term related about the theta, so you have both around T around the theta term and round V around the theta term as well. Okay, so take a derivative of kinetic energy with respect to theta dot has this one, the first one has a derivative term, second one which has 2LC cosine theta, and this doesn't has a theta dot related term, so you don't have to consider about that. And you also have a theta dot term derivative here. So you have three terms here, right? And then once you obtain that, you have to take another derivative with respect to the t, so that you can end up having theta double that term here, and here you have a chain rule. Take a derivative of the theta with the derivative with respect to the time t for the theta and VO respectively. So you have ended up getting acceleration term here. And you can also have a theta double that term for the angular velocity term. So finally, you ended up having all these terms. Okay. Now, let's take the derivative of the kinetic energy with respect to theta. So the only term that is related about the theta is the term in the middle, right? So you can take a derivative with respect to theta. So what you can have is MLC theta dot V naught, VO, okay? And for your potential energy, you have a mg cosine theta. So here you have a minus mg sine theta. So you just, put them together for the Lagrange's equation term. What you can have is I theta double dot and moment equation by the current acceleration and moment equation by the gravity. Okay, pretty much similar to what we have worked on in the previous case. And suppose that there's external torque applied at the ankle, then your Lagrange's equation should include a generalized force term, torque term here, and that will actually add a torque term there. So this is exactly equivalent to what we have obtained using the Newton-Euler equation, Newton's law, using the free body diagram. So those are equivalent. So either way, you can apply to obtain the equations of motion, but personally, I would strongly recommend you to work on with the Newton's law, draw the free body diagram, obtain the equations of motion for each segment and combine them, and check your answer whether your answer is correct using the Lagrange's method. Okay, so double check your answer using Lagrange's method. Okay, so you can also apply Lagrange's method. Actually, it's more useful for handling more complicated system because Lagrange's equation is a relatively easier approach, personally, I think, than the Newton's methods. So Lagrange equation for the multiple joints, you have to, now define the two generalized coordinate here for the lower segment and the upper segment. So it will be maybe theta 1 and theta 2 describing the tilt angle for each segment. And the thing is, should I then put the relative reference coordinate at pelvic point, or should I set the reference coordinate to describe the upper segment at the ankle? Which one should I use? Well, in the Newton's method, when you are putting the relative coordinate frame, the only thing you have to consider is the inertia force, right? However, I would recommend to use the absolute. Oops, the underline is a little bit off. Use the absolute coordinate frame to describe the position for the second or the upper segment. The reason is coming here. Okay, suppose you have set it up the generalized coordinate at theta 1 and theta 2, and next step is you have to formulate the kinetic and potential energy. The kinetic energy for the segment 1 is what we have just worked on in the previous slides. And for the kinetic energy for the second one, you will have mv square plus I omega square, right? But for the mv square here, the v should be the absolute velocity, right? The energy. It should be described as absolute velocity. Therefore, maybe you do better formulate the coordinate in terms of absolute coordinate frames so that you can just use those value and its derivative to formulate the kinetic energy for the Lagrangian. Okay. Same for the potential energy. Gravitational potential energy for the lower segment and the upper segment could be expressed this way. And you can just plug that into the Lagrange's equation and obtain the equations of motion for first segment and second segment. And note that you have two generalized coordinates. So you have a derivative for the theta 1 dot and theta 1 here, and then theta 2 dot and theta 2 here. So you have two sets of equations of motion that will establish the equations of motion for 2 degrees of freedom.